Okay, so we have exam coming up. It's going to be on the first. Okay, so that means not this weekend, but the weekend after, we'll have a practice exam review. And I'm a little behind in the homework, so this lecture is going to be a little short because I'm getting a either I'm getting behind in the homework or I'm getting too ahead in the lectures. Your equivalent, I suppose. But so this is like going to be a little short lecture, but I'm going to try to catch up on the homework because we're like on homework 19. So I have to do like three more. So I'm gonna do like today, Saturday, and Sunday, and then so you'll be able to catch up during this week on the homework that we're behind on. They're not all going to be doing the same day, of course, but I need to catch up because the idea is our exam 1 was on chapters 10 and 11, and so exam 2 is going to be on chapters 12 and 13, and we'll be finishing up 13 next week. Okay, so that's the reason for that. Yeah, okay, so for review, for lecture 21, we went over the astable multivibrator, and we saw that what we can do with this multivibrator is use a comparator, and these comparators have this interesting property where they have a very high slope right here. And yeah, so I was talking in the office with one of you guys, and we were actually discussing this. So typically, the amplifiers have a voltage transfer characteristic that's sort of like this, right? May have some V offset right here. Here's some VCC and some VEE. Okay. And so the thing is that this slope is, is pretty high usually, but there's a huge space, a huge range, that you can have your input at before it starts to saturate for the output. So these comparators, they have a much larger slope, right? Right, so such that if you're just a little off, that's all it really takes to totally saturate to the to VC or VEE. Okay, so that's why the difference between those, it really matters, and that's why you get this this very abrupt saturation. Only because you have such a narrow width to operate over, and so that sort of tendency to saturate very quickly, either high or low, allows this to turn into an oscillator, because what you can do is then use the saturation voltage out here and then feed that back to sort of change if this saturates high or low for the next state. And so this capacitor is put in here in order to allow some time to pass before it switches to the other state for saturation, because you're having this RC time constant between that. And so here's the saturating really high, here is saturating really low, but this time right here has to do with the RC time constant. And you can make this smaller or larger, that duration, by changing these values, by increasing or decreasing both or either or RC. And so you can see where this capacitor is like charging up, discharging, charging up, discharging, and that's how you get the oscillation just from this comparator type of op amp. Okay, we also looked at the monostable multivibrator, right? And so what was done here is that we've taken the astable multivibrator and then we added some diodes to this to control the flow of current. And so what happens here is that as long as it receives a pulse coming in, then it'll start charging up. And that's the unstable branch right here, charging up. And it'll charge up to a certain value before it then crosses before this value right here, then exceeds that value, and then it starts decaying after that. But then it'll stay down here. And the reason why is because the diodes, they're controlling the flow of current. Okay. Another thing we looked at was the analog frequency generator. And here, since we know how to oscillate using op amps, we are able to have this astable multivibrator to give us this rectangular wave right here. And then we can integrate that to get a ramp out of that instead. And then we can filter that ramp through a low-pass filter and filter out the high frequencies and turn the ramps into sort of like rounded curves that's sort of sinusoidal. We also started looking at the BJTs and MOSFETs, and we saw the characteristics of those. And we're going to continue on more today. So for today, we're going to concentrate more on BJTs, and then on Monday, we'll deal with the FETs in terms of small signal analysis. Okay, so in lecture 22, we looked at the DC blocker, right? And we found out that for some voltage input, you're going to have some DC and some small signal variation around that DC. In this case, it's sinusoidal, right? The DC blocker is applied here, and so what that does is sort of, well, it blocks the DC component. So even though you do have a DC offset, the voltage that you get right here is centered around 0. Okay. And also, we have an AC bypass. And so what the AC bypass does, that in terms of AC, you have this sort of like a virtual ground that can sort of bypass around this resistor to get to ground. So that was a point of that. We also started looking into analysis and design method. Oh yeah, I think I was pronouncing this wrong last time. I think I said it's quiescent. I think I said, did I say quiescent, or I forgot how I pronounced it last time. But it's quiescent. I have to make sure I got that right. So anyway, so what you want to do is break it up into DC analysis and AC analysis. So for DC, you find the equivalent circuit, replace their capacitors with open circuits, and you replace the inductors with short circuits. Okay, and of course with the AC you do the opposite. You replace the capacitors with short circuits and the inductors with open circuits if you have those. And we also look at the diode. We're going to do a little bit more of that today, looking at the diode. And well, actually, not really the we're going to look at something that looks a lot like this right here. So we're going to borrow that information that we got from the diode. Yeah. So, but we dove into the diode. We looked at some of the parameters and how it behaves, and we did our first small signal analysis on the diode, and then we're going to carry it on to the BJT. Okay. Okay. So here are the topics we're going to talk about today: small signal model for the BJT, the hybrid pi model, which is the most popular, graphical interpretation of transconductance, and small signal current gain, intrinsic voltage gain of the BJT. Okay, so so a little bit about transconductance. Okay, just to remind you guys. So we know about resistance, right? So resistance is voltage over the current. Okay, and conductance is the inverse of this. Okay, so now this is transconductance, and it's typically applied to a situation like this, where you're looking at your two terminals. It's like a two-port. So you look at these terminals right here. It's the output current right here divided by the input between these two terminals right here. So it's slightly different definition than over here. So this conductance is called transconductance. And also, resistance is just the inverse of this. Okay, but it has to do with the current output right here, change in that over the change in the the voltage input. Okay, so let's get on with small signal model for the BJT. So, so here's this two-port representation. So here's BJT right here. Now this is the voltage between the base and the emitter right here. So emitter and the base. And this right here is the voltage between the collector and emitter, collector current, base current. And so you can model this as a two-port, okay, where this voltage across these terminals is still right here, and same with the current. And the voltage across these terminals right here, the voltage CE, is the same as right here. Now what goes inside here, you have this R pi right here, and over here you have this RO. This is a voltage-controlled voltage source. I'm sorry, a voltage-controlled current source right here and here. This one is proportional to G mu, and this one is proportional to GM. So here's transconductance right there. And here are the Y parameters for that. And so for the signals about the Q point, as we discussed last time, when you have everything in capital, that is the DC for the Q point. And here's the perturbation around that, that Q point, right? Typically sinusoidal, right? And here's the sum of those. So the sum, so the small signal is all lowercase, the DC all capitals, and the combination of the two, both lowercase and capital. Okay, so you can do that for the voltage and the current for both the base and the collector. Okay, you can also write it like this, where this the voltage between the base and the emitter right here could be, I'm sorry, this right here can be written like this, which is just delta VBE. So that's another way to write that. Okay, so for the Y parameters, in terms of small signal voltages and currents, you can write it like this, which of course makes a lot of sense, because if you see this, this G pi right here, if you make your voltage CE, if you make that 0, then this term goes away. And so this G pi is just this quantity right here divided by VBE right there. Okay, and of course you're evaluating at CE, at VCC being 0. So this term goes away. And you can do that with all of them, right? So for GM, for example, you make this term right here go 0, right? And so your GM is just this IC over VBE. And same with G mu and GO. So that's how it's typically done. Another way of doing it is evaluating it around the Q point, okay, for all of these. So if you do that, you're just doing the differentials of how does this value change versus this value. And the ratio of that at its Q point is the same as this right here. Okay, so do you guys understand this partial differential right here? So basically, when you do partials, you're varying one parameter, and the other ones you're holding constant, and so they don't show up because they're being constant. Like for example, if you're varying this value right here, if you take the partial or the derivative of this whole thing right here, this right here is assumed to be constant with respect to that, so that term doesn't show up. Okay, because it'll be 0. So in effect, you're doing the same thing, but you're doing it with partials. as you're doing right here. Okay, so so a lot of this stuff stems, the book says, from chapter 4 and 5. I guess that's from Digitron. Okay, so that's where these a lot of these equations come from. Do you guys recall any of this stuff at all? A little, some of you. Kind of. Okay. Okay, so what we'll do is we'll take these as definitions, as what these quantities are. Okay, so now we've seen this thermal voltage, and we've seen the voltage between the base and emitter. This VA right here, I found a good plot online that explains that. So this is called the early voltage, and the person who made that, that's their last name. That's why it's capital. So it was James Early over at IBM. He's credited with this, and but it makes sense too, because if you take these lines right here and extend this out, they all intersect right here, which is sort of like an earlier voltage. So it sort of makes sense. But so just, I guess, convenient coincidence. So this VA, the early voltage, is typically between 10 volts and 200 volts. Okay, so there's a negative on that, right? So that's going to be around 0 volts right here. So this is like negative 10 to negative 200. That's where this point is right there for typical values. Okay, so again, this is the collector emitter voltage, and that's the collector current right here. Okay, so that's sort of like plotting this equation right here. Okay, now this beta F, this is the Ford common emitter current gain. That's what this beta is. And I got this plot from chapter 4, chapter 5, 4 or 5, where it first introduces it. Okay, so this is beta F, okay, as a function of frequency. Okay, so and we'll see how that plays between the FET later on in the lecture. They're quite different, but that's the characteristic of that. And this beta FO, it represents the value of this common emitter current gain extrapolated to this VCE being at 0. Okay, so using these equations right here and basically applying it to our model, right? Because this is just a very general model, and we could use it for many things, but we're going to apply it to this in particular. Okay, so basically we have to find out, well, what are these parameters? What are the Y parameters for a BJT? So that's what's being done here. So this is very general. Okay, you can apply this to any kind of component you want to put in there, or system you want to put in there, but then you have to figure out what it is by using its model. Okay, so in this case, partial derivative of IB with respect to VCE, that's going to be 0. So that means here, that's going to be 0. So there's going to be, this is going to be an open circuit. So that's going to be gone. But the other terms survive, as you can see here. And they're worked out to their own values. I guess the values you want to remember are these right here. Are the ones you want to use at least. Okay. Oh yeah. And this transcondensance right here, G pi, you can. It continues on the display page right here. So this is just some reduction. And so what the book does, it takes this expression right here, and then it just groups up all of this and that beta F into this beta 0. And so beta 0 is this expression right here. Okay, and so this beta 0 represents the small signal common emitter current gain of the bipolar transistor. Okay, so here's our model, right? And so now we can convert it to this. And so the big thing here, like we were talking about, is that this term right here, that transconductance is 0. So you can eliminate it from your model. Okay. And so what the book says is this. That is actually the hybrid pi model. Okay. And so the book explains that this is the model that is most commonly used. So if you read about it in a journal, or if you read a journal and they're talking about modeling the BJT, they're most likely going to use this model. And the book says it's used so often that you should memorize this right here. Okay, so for the transconductance right here, since it pops up so often, 40 IC. Okay, you should memorize that. For the input resistance right here is beta 0 over the transconductance. And for the output resistance, it's just, of course, 1 over that. And it's going to be, if this term is really small compared to that, then it's just your early voltage over IC. Okay. The most important quantity of all of these is your transconductance. Okay. It says here it's the most important small signal parameter. It characterizes how the collector current changes in response to a change in base emitter voltage. Okay, that makes sense. And so we're really talking about this right here. Okay, now this looks a whole lot like our diode. Okay, but it's the BJT. Right? And that's probably why the book talked about the diode first, small signal around that, because, you know, like all this stuff, right? So this transconductance right here, that's the slope of this. Okay, so just like the diode, you have your Q point, your quiescent point right here. And what you're doing is that's where you set your DC up, and then you're going to do your small signal variation about that. And then if it's within a certain value, like about 5 millivolts, like this BE, if that goes as high as 5 millivolts back and forth, then what happens is that it linearly transfers to the current without distortion. Okay, but within that small range of values. If it's larger than that, it'll go over, but you'll have some distortion. And for example, if you put in a nice pure sine wave, it won't come out nice and pure. It'll be slightly distorted. It may experience some cutoff or a little bit of morphing or something. But then, of course, based on what we know about Fourier series, you can represent that with just some higher order harmonics. Okay. And so for the DC current gain, beta F, for a real transistor, it's not constant, but it's a function of IC. Okay, so this is what this looks like. So this is the DC current gain as a function of IC coming in. And this value IM, that is the collector current at the maximum beta F right here. So this is the beta F curve right here as a function of IC. So that max right there is for IM. Okay, so this right here is the AC current gain. Okay, so remember this is the DC current gain, beta F. Beta 0 is the AC current gain. Okay, there is some beta F in there, but it behaves slightly differently. So if your IC is smaller than IM, that max, then your AC current gain is actually greater than your BF, which is being plotted here. On the other hand, if your IC current is greater than IM, then your AC current gain right here is less than this BF right here. Okay, And the book also says that typically they set these values equal to each other. But if you're going to do some really detailed analysis, you probably don't want to do that. But if you're doing some quick analysis, I guess you can set them equal to each other. The values over here aren't given, so you don't really know how much change is happening. It could be a very small change, and that justifies them setting, most people setting these things equal to each other. Okay, so another important relationship is the intrinsic voltage gain, this mu f right here. Transconductance again pops up. Is equal to, if that voltage VCE is small, then it's the early voltage over the thermal voltage. And at room temperature, this intrinsic voltage gain is typically about 40 VA. Okay. The intrinsic voltage gain, mu f, represents the maximum voltage gain that a transistor can provide. It's also referred to as the amplification factor of the device. And for example of ranges, for an early voltage ranging from 25 volts to about 100 volts, this mu f amplification factor ranges from 1,000 to 4,000. So that's pretty huge. All right, for the last slide here, so here's a table that looks at the variation of small signal parameters with operating point. So here's some IC, various amounts of IC coming in here. You can see how things change. So here's the transconductance. Here's R pi, RO. And you can see how they change. And they're changing by a lot, right? Orders of magnitude change, which is, yeah, quite interesting. Now, this mu f, as you can see, it doesn't change at all. Okay, but that's for the BJT, and the book says we'll find out for the FET that's not true. This is a function of IC for the FET, but for the BJT, this is pretty constant. Okay. All right. Any questions about this stuff? Okay. All right then. All right. I'll see you guys Monday.